And today our speaker is Qingsong Wang from Jilin University with the talk Conditional Self-Intersection Measures of Brownian Motion. Please, Qingsong.
Okay, thank you very much, Professor. It's my great honor to give a talk here. Today, my talk is based on my PhD thesis, and it's jointly work with Professor Andre. Okay, so let's begin. First, I will introduce about the motivation. That in physical and chemical science, people usually will consider the uh, use the random curve to describe polymer. Uh, the polymer will change with the time. Uh, the polymer will change for several reasons. First, there are flexible chemical bonds between monomers. Second, there are influence of external force, like the random contacts with media. Last, there are interaction between different parts of the polymer. So since polymer has this random shape, people model these long linear polymers using trajectories of some stochastic process. Here I show an example of polymers. Here's a picture of DNA, and DNA is a kind of polymer. Then the shape of this trajectory of a well-studied process like Brownian motion, it was very complicated because we know it's not differentiable. So it's naturally arise the question when we're modeling the trajectory is non-smooth, how to characterize its complexity. The aim of our investigation is going to describe the simple geometric structure arising in Brownian trajectory, and we'll study its evolution with the time. And here's the outline of today's talk. First, we will say about the visitation measure and the self-intersection local time and its asymptotic results. Second is about the polygonal line inscribed in the trajectory. This part will discuss the polygonal line almost inscribed in Brownian trajectory, and we'll talk about the anticipating boundary value problem. The last part is for the evolution of the random curve via equation with interaction. In this part, we will discuss the limiting behavior of visitation measure. So let's begin with the first part. And now let's see the definition of the visitation measure. First, we use some description of linear polymer, which is we define this random curve parameterized by this psi, which from 0, 1 to RD, which is a continuous random process, and denote the curve to be gamma. Usually, psi is non-smooth, and gamma will have complicated structure. In this case, one can characterize gammas by its visitation measure. The visitation measure can be defined as follow. First, in one-point case, the mu1 of delta, which is a Borel set in RD, which can be defined as the integral with respect to this indicate function of psi t. And for multiple case, the delta is from the Borel set of RD multiply k minus 1, and is equal to the multiple integral and the indicator of this multiple minus. And with this definition, next we will present a asymptotic behavior of the multiple self-intersection local time under some condition. Here I give a picture of this condition. It's not very beautiful, but it's just a handwriting picture, but it tells us what this condition means. It says that the trajectory of Brownian motion during time 0 to 1 will visit this point v1, v2, v3 during this interval 0, 1. This result is considered W to be a R2 valued Brownian motion, and we give the symptotic of this conditional expectation self-intersection local time. Under the condition Brownian trajectory visits this v1 to vn, it will be equivalent to the constant 1 divided by pi multiply the minimal of this mu k prime plus mu k minus 1 prime in power minus 1. And next, I'm trying to show some part of the proof, but it's not all of them. I will show just only for one simple case. Here, we'll first define xt, a process as a polygonal line which connects these vertices 0, ws1 to ws(n), and we will divide our Brownian motion to be two parts, yt and xt. Xt is a polygonal line, and here we can prove that xt and yt here are both integrators. Here, please let me mention that integrators are central to Gaussian process, but I will give the precise definition later. And we can also prove that here these two processes, xt and yt, are independent. Here we will just give the proof under the case that here's only one condition, that w1 is equal to v, not for multiple points. So in this case, one can define xt to be the t multiplied w1. And in this case, we can see that yt is actually the Brownian bridge. So this is somehow interesting example. Okay, under this case, one can rewrite our initial conditional expectation as follow. It's a double integral with respect to the density of delta y. And next, we can just do a change variable of s1 is equal to t2 minus t1, s2 is equal to t2 plus t1. And we can rewrite the integral to be only 1 because another with respect to s2 can be calculated as a constant. So we'll get our initial conditional expectation to be such an integral. And then next, we still do a change variable to change the power of exponential to be a new variable. In this case, under this change variable, it will split our integral interval 0, 1 to be two parts because of the special form of this s1 multiply 1 minus s1. But these two parts will stay the same. So finally, we can get under this change variable, we will have this integral. And for this integral, one can use the dominant convergence theorem under the condition that the minimal vi tend to infinity. This integral will tend to some constant 1 divided by pi. And so we'll get the desired result that our conditional probability will equivalent to this constant multiply this vi, and this is exactly the result what I showed here. I only showed the proof for one conditional case, but for multiple dimension or multiple point case, it will be similar to it. I don't show it here. Then next, I will tell something about the polygonal line and with connection to the shape of the curve. Here we suppose our curve is parameterized by the continuous function phi. Here we consider in R3, it's connected to our real world. For the points u1 and un, we fix it in space R3, and we denote the gamma u1 to un to be the polygonal line which connects this point u1 to un. Okay, now the polygonal line gamma u1 un, which is inscribed in the curve in the condition that there exists a partition T1 to Tn, which is during 0 to 1, such that the function of Tk, which is actually equal to Uk. So what it means, here I give also not a very beautiful handwriting picture, but it can show us what it means. It just says our curve will visit the vertices of the polygonal line during the time interval 0, 1. It says such a thing. Next, the polygonal line gamma u1 to un, which says is inscribed in the curve up to the epsilon. If here exists still the partition T1 to Tn during 0, 1, such that the phi of Tk will belong to the ball with centered Uk with a radius epsilon. Also, I give a picture which says that the curve around the curve we will visit the ball with radius with centered UK and with radius epsilon. We'll visit this ball during time 0 to 1. We say it is inscribed in curve up to epsilon. Then we define a set z epsilon, which is a union of the ball of zk epsilon. And here we suppose that the intersection of the different ball is empty set. Then with every gamma u1 to un, which has a vertices from the set z epsilon, the sequence of number alpha 1 to alpha n can be associated. This associated is that the uj belongs to the ball of z alpha j epsilon. So now if the polygonal line satisfies this condition, in this case, we'll call the polygonal line has a type of alpha 1 to alpha n. Based on this, we'll get the definition that the curve alpha has at least of type alpha 1 to alpha n if the polygonal line of such type can be inscribed in it. So this is the definition, what we will need later. And then I will show a result. Here I will show the result is a symptotic behavior of the probability that the polygonal line can be almost inscribed into the Brownian trajectory. Here we consider the case is the dimension is greater or equal to 3. Bt is the Brownian motion. We fixed the starting point x and z1 to zn. Also here, the z1 to zn is different from x. Then the probability that the Brownian trajectory almost inscribed in this polygonal line have such a symptotic result under the condition that the epsilon is 10 to 0. Here, I will also show part of the proof, but still only for simple case. That we will just give the proof for the simple cases. Here, just one ball. To deal with it, we just need to use the scaling property of Brownian motion. We can rewrite the probability in this form. And we write inequality divide this event to be 2 parts. So it will greater equal than 1 probability minus another 1. For the previous part, it's already some known result in the book of Brownian motion. that this probability has a asymptotic result when epsilon tends to 0. So next we just need to investigate the second part of this. To investigate this, we will use the Markov property to do some rewrite, and by some calculation, we can get the probability can be written as such an integral. So now we get the explanation of this probability. Then what we need to do is just to consider the asymptotic result when epsilon tends to 0 and use the previous result to minus this one and take epsilon tend to 0. We will get the asymptotic result for the initial probability. And here the proof is only for a simple case. Next, I will talk something about the anticipating boundary value problem. We'll consider the heating time and the heating probability for the special class of Gaussian random process, which are called the integrators. And this process were introduced by Professor Andrew for the purpose related to the theorem of stochastic integration and anticipating stochastic differential equations. It was discovered that the integrators can be used to model linear polymers such that the important characteristics as local time of self-intersection were also studied for integrator. Here, these two research also do some research related to these topics. If someone interested can check their results. Okay, so next we're going to give the definition of integrator. Like I already told, integrator must be centered Gaussian process under the condition that there exists a positive constant grid C, and for arbitrary partition T1 to T0 to Tn during 0, 1, and the real numbers satisfy such an equality. And what this equality will tell us, it's telling us that for the function belongs to L201, then the integral of function with respect to our integrator is always well defined as a limit in the square mean. So this is what this condition tells us. And moreover, there's an equivalent definition, which is also very important and very helpful. If there's an integrator, there must exist a winner process and a continuous linear operator, such that the integrator can be present as the integral of this linear operator and the integral with respect to the winner process. So it gives a relation between our integrator with a linear operator. Next, I will talk a little about the boundary value problem of winner process. If we consider the start point x belongs to the domain we denote to be D, and here we put a function wxs. It's also connected to this time t, which can be seen as a function of this process, and also with the time t, which is defined to be 1 if this process can be reach the boundary. In the opposite case, we define it to be 0. So in this case, the expectation of this wxs if we denote to be UTX, it's of course the probability that the winner process it hits the boundary up to the time 1 before time y. And it's well known that this function is satisfies this equation, the boundary value problem. But in general, not as we know that the Brownian motion is an example of integrator, but in general, our integrator has no macro property. So in this case, our integrator may cannot get a parabolic problem. But here is still an approach which will allow us to get a series of desired probability in the, this is probability we'll investigate later. We'll express this as a series. Before to show the result, we'll first introduce some definition. First is about the Ito-Wiener expansion. That for every square integrable alpha, which from Wiener process W, it has a unique Ito-Wiener expansion. Alpha can be expressed as this infinite sum and multiple integral with respect to this coefficient and WT1 to WTN, where this coefficient must satisfy these conditions. The expectation of alpha will exactly equal to A0, and this square will express as this form. This is what AN is. Next, since we have the Ito-Wiener expansion, we'll give further definition. For AN here, one can consider it as an element of tensor product. So here, if we consider for the continuous linear operator C, one can define new functions A and C, which is equal to the C to the tensor power n multiply AN. So now, if we assume that the operator norm of C is less or equal than 1, then one can get a new series we defined as gamma C alpha, which express is similar to the Ito-Wiener expansion, but here we replace AN to be ANC. And also here, this expansion is also convergence in square. And here, this new operator is also continuous and linear. And we call this gamma C is the operator of second quantization related to C. Now we know what this second quantization operator, and then we will show a very helpful result of second quantization. If we consider two independent Wiener process, we denote to be W and W prime, and for operator C satisfies the initial condition that the norm is less or equal than 1. Also, we can define another operator is the square root of I minus C star of C. Then, with the help of these two process and two operator, one can define a new Wiener process. We denote to be W prime, which is equal to this integral plus another one, but it's still a Wiener process. And then what we can get the second quantization of alpha with respect to W, which can be expressed as the conditional expectation. So what this lemma just tell us that there's some connection between the second quantization and the conditional expectation. It will be really helpful for our result. So with this lemma, what we can do, if we suppose here's a function phi which from C01 to R is bounded and measurable. Like before, we considered an integrator construct with the help of C and another integrator Y which construct by the operator R, just like the lemma says. Then if we consider the expectation was phi x, first we rewrite this to be a conditional expectation. And by the lemma, which is actually tell us this conditional expectation can be expressed as a synced quantization multiply this function. So this is what exactly we will do next. Here's some basic knowledge that, but it's almost similar than before, that there are two continuous linear operators C and another one is R satisfy such a condition, and we can construct integrator with the help of this operator C. Also, like the boundary value problem, we denote the WXS, which hits the boundary is equal to 1 and not hit boundary equal to 0. We can get our probability such that the integrator hits the boundary, and this probability can be expressed as the synced quantization multiply this Wx0 under the condition W equal to 0. To prove this, we will start to consider this one. First, it's a continuous function with respect to the variable, which is Gaussian, but with respect to W prime. And by the quality, the conditional expectation is actually equal to the synced quantization with respect to this. And we can say that if we take this condition probability, this gets the desired result. Next, we will show the expression. What we can do get a series of our probability of this one. First, we need the help of the linear expansion of Wx0. We define its kernel in this form, and we can denote this GXRN is equal to the operator in tensor power D multiplies multiply N. And one can define the coefficient of linear expansion alpha, which has a coefficient as a coordinate of this GXN in the basis E1, EM in Hilbert space. Then we will get such an expression. Our initial probability will equal to this series of the sum. Maybe it's not so clear that what this alpha, the coefficient, says. Next, I will show an example of how it looks like. This example will just only consider in the case that the dimensional is equal to 1, our initial probability can be seen as this. And here, if we do some rewriting of it to be in the element of the basis of E1 to n, we'll divide this to be two part, or the one part can be is this, and it is exactly can be rewrite as a Hermite polynomial of xi1 to xi. And another one is exactly the coefficient. Satisfy such a form with the initial coefficient an. So this is the result. What this alpha can be expressed. This is only just an example of it. Okay, now we turn to the last part of the talk today. I will introduce the equation with interaction. The equation with interaction was firstly considered by Professor Andre, and the equation was introduced as follows. One can see the most different part is that in the coefficient A, here is a mu t, which is a measure. Also here in the coefficient of B, here is a measure mu t. Here we consider the initial definition considered not only for Brownian motion, but here is considered like the winner sheet. Since the coefficient contains a measure, we need to understand how to consider its distance between measures. Here we will use the Wassiston distance. The Wassiston distance is defined to be the distance between the probability measure, which is defined as this. This distance is defined as we consider the infim of the joint probability distribution of mu and nu, and calculate this integration. Now let's combine the initial definition that if we think the mu zero to be the visitation measure like I introduced before of a curve gamma, then one can imagine that the mu t will also be a visitation measure of its image at moment t. The same as for psi s, we can consider the mu t is also visitation measure of field this. And mu t, of course, can be considered as measure in the equation sentence to us. It means that the motion without separate points, it depends on the shape of the whole field. So one point will depend, the motion will depend on the whole space. This dependence is described by the coefficients that contain the visitation measure. So here I give two result of this xi, which defines the solution of equation with interaction about xi(s) with respect to t. For this new process, which we can prove that xi t is continuous firstly, and xi t also is Markov process in the space C01 RD. But because of time, I don't show the precise proof of these two lemmas. Since I told that I told here, the dependence is described by the coefficient. Next, I will show a special form of the coefficient, and I will present some result related to this special form. Here we consider the whole space RD is defined as the union of connected domains dk, and we assume all this dk, the inner part is in the intersection of the inner part is equal to the empty set, so it means they will not intersect. And for every dk, we take one point zk in the inner part of dk. Then we'll try to define a function, which is C1, and it satisfies the condition that in the boundary, in every boundary, this function will always equal to 0, and the function v and the v prime, the derivative of it, is bounded on Rd. And this function must satisfy that with the help of construct of v to get the Cauchy problem in such a form, the solution of this Cauchy problem will turn to zk that we take in every dk when the t is tend to infinity. So it means when time tend to infinity, that the solution of this problem will attracted by this zk. Then we define another function which is non-negative that also is C1, and also take value for all the boundaries equal to 0, but it is non-negative, so in the inner part it stays always positive. Then with these two functions h and v, we define a new one which is just multiply over h and v. Then with this f, we define the coefficient a in such a special form. It's equal to the sum of for all the n and indicator of decay of the integral of for any decay, the f with respect to the measure mu. Then the coefficient constructed in such way to describe the motion particle in media, which will always attract by this z because of the condition. So with such a special form of the coefficient, next we will show that if we start from any mass distribution, then the measure mu t will be concentrated in the points zk, will concentrate in the attractors. Yeah, this theorem says, here the theorem consider only that not a stochastic case, but the A is in the special form what we defined. Here, if we define this pk is equal to the mu0 of dk, then we define nu to be the sum for any n that pk multiply the delta function with k. Then we will have the Wassiston distance between mu t and nu is 10 to 0. And I didn't show the precise proof of this, but I will talk a little about the idea how to prove this. Here, by the property of the Wassiston distance, if you want to prove the two measures distance is 10 to 0, we just need to use to prove that the two measures are weakly convergence. So here we just need to prove that mu t will weakly convergence to nu. And this is can be proved by But the truth that when t tends to infinity, the solution of this equation will tend to the attractor CK, and we can get the weakly convergence. Okay, next we will present another theorem that about the random curve in the flow with interaction with attractors like we defined before, Z1 to Zn. And we will investigate the probability of this. The random curve has at least type alpha 1 to alpha n. And this probability will less or equal to the lower limit when time tends to infinity. Yeah, this is a theorem. First, we will denote the initial random curve is denoted by this gamma 0r. And we'll have the gamma t, which is driven by the solution to equation with interaction, and which is satisfies the coefficient A in special form or what we defined. And then for sufficient small epsilon, of course, there is for zk epsilon will belongs to the domain dk, the inner part. Then, if we define a function, here we denote to be RT, which is in fact the probability that the gamma t is at least of type alpha 1 to alpha n, then it will have a property like I said, this RT will less or equal than the lower limit when the time tends to infinity. Here I also don't show the precise proof of this result. I will say about the idea of the proof. Here, in fact, our function is in fact a probability. If we consider this part to be an event, the idea of the proof is try to find another event. If we think this to be event A, we will need to find event B, which is included in A, but this event, when time tends to infinity, it will tend to the initial point. Oh, exactly here, this one. And what we'll get, a new event which is always included in the initial one, but its limit will tend to our initial event. This exactly tells us this result because you consider the left part to be the limit of our new probability, and it will always less or equal than the initial probability. And of course, if we take the lower limit, of course, it will stays less or equal. So that's like the hint of the proof here. Then next, we've seen that the distribution of the mass tends to attract the point of the differential equation with the interaction. Under this, we will investigate now the visitation measure of random curve in the flow with the interaction. Before it, we will note such a sequence of set, which is a ball with centered of zeta alpha 1, alpha 2 minus zeta alpha 1 with radius epsilon, a sequence of I. Then, like previous result, we still use the special form of A. Also, here's the initial random curve we denote to be gamma 0 R. If we assume that this initial curve has at least type alpha 1 to alpha n, then the visitation measure mu tk We can also get the random curve gamma t with the help of the solution with of equation with interaction, which can be obtained as a solution with it. And for this visitation measure, we assume it has density we denote to be LKT with respect to the Lebesgue measure. And so suppose that in the initial time t equals 0, the visitation measure mu 0, 1 of for all the boundary d is equal to 0. Then for any epsilon greater than 0, we will have the integral of this density is 10 to 0 when t tends to infinity. To prove this, I also still just talk about the simple case. Here we consider the k is equal to 2. In fact, the integral of the density is exactly the visitation measure of mu t2, and it can be expressed as this double integral in this form. And if we consider that this process psi t2 minus psi t1, if it belongs to the set E1, it will of course means that the model of this difference is less or equal than epsilon. So what this condition means, this exactly tells us that the process will attract by these two sets. And this is exactly what our assumption will lead this when t tends to infinity, what it will be. So it means the visitation measure concentrate on the ball, on these two balls. And so it will make that the visitation measure is concentrated on the set E1. So this visitation measure when t tends to infinity will tend to 0. So this is a proof for simple case, but for general case, it's more or less the same. Next is some reference of some related work. If someone is interested, one can check this related work. And this is all of my talk today. Thank you very much.
Okay, thank you very much for presentation. Maybe somebody have questions or comments, please. If not, then let me just have some comment that this is almost all material from Qingsong PhD thesis. And the main idea, as you have seen, is to try to characterize the evolution of random curve in the random media with some simple characteristics. I must say that visitation measures maybe are appropriate tool for describe the geometry of the visitation measure, but it looks like uh, that we have to understand what happens with it, and when curve is evolving. And it occurs that we have to do a lot of things. Firstly, to understand some like numbers, so real valued or RD valued characteristics of visitation measures. It was done using these expectations and conditional expectations. Also, we have to calculate the probability that we can organize some simple structure in our trajectory. And it was done in the second part of the thesis. The evolution of the random curve is discussed in the third part. So we hope that we will continue this investigation, but for now, that's all what we are presenting. So thank you, Qingsong, for your presentation. And maybe Georgi know who is the next speaker.
Next speaker will be Vlada Dimic.
I see. This is maybe about random graphs, yeah?
This excursion representation for stochastic block model. And maybe it will not be in Zoom.
Please, yes, pay attention to this and inform us before the seminar, yeah?
Yeah, I will inform you as soon as she will inform me.
Okay, yes, I remember that she has some problem with it. Okay, good. Then thanks everybody and see you next week. Bye.
Okay, thank you very much. See you next time.
So,
Okay, bye.
good night. Bye.
Thank you. See you.
Bye.
See you.